right, this set of notes, we're going to talk about orbitals. So I wanted to start you off with this picture. In the last set of notes, we were talking about electrons and how electrons are a little bit more complicated than we learned earlier. They're not quite the simple Bohr model. They have a lot of interesting properties, and we're going to kind of dive more into that to give us some background that we'll need in order to proceed forward. Okay, so these are all diagrams that show where specific electrons, so actually this is the hydrogen wave function. So if we look back at the periodic table, we'll know that hydrogen has one electron. These are the different places or orbital shapes that that one electron can take. And so when we're looking at this, this is kind of that wave particle duality of the electron. This is the space that this given electron can exist in at a certain energy level. So depending on how much energy this hydrogen atom has, this electron is going to take one of these shapes. And we're going to look in just a second and see that these shapes are in fact orbitals. Okay. Like we talked about before, electrons exist in areas of probable location. This is not an orbit. An orbit is like, the way that the Earth orbits around the sun. It's a way of knowing the locate, like we can know where the Earth has been at different times and locations. Electrons aren't like that. They pop in and out and just flit around with physics that doesn't quite make sense to us on an intuitive level. But these are the shapes that we've noticed that emerge when you try to figure out where electrons are located at any given moment. They're somewhere in this area. The shell or orbital level is the relative distance from the nucleus. We've already kind of learned about this in Bohr models, where we talked about how the first shell is closest to the nucleus, and then there's a second and third and fourth shell, and each shell can hold different electrons. This model, this quantum mechanical model that we're going to study today, explains that essentially, because it's actually a little bit more complicated than just straight up orbitals. Every orbital has suborbitals, or these extra shapes that are inside of them, and the electrons are in one of these in these orbitals. So the orbital shapes of the valence electrons determine its properties. We're not going to get into this too much, and in AP Chem we can get into it a little bit more. But for scientists, for chemists, it's really important to understand these suborbitals because it helps explain how different elements bond with each other, different atoms bond with each other, and a whole bunch of other just different properties of that nature. So, sorry. Okay, so these are the suborbitals. Within each orbital, so within each shell, there are these different suborbitals, and each suborbital can hold a different number of electrons. There's a very specific order in which the electrons fill, and it's based on energy. The electrons, it's most energetically favorable, or it's better for them to be as close to the nucleus as possible. So depending on how many electrons a particular atom has will determine which orbitals and suborbitals and shells and all of that the electrons live in, that they exist within most of the time in their ground state, or most relaxed, most energetically favorable state. Eventually, we are going to get to, in the next set of notes, we're going to get into how to record those, where all those electrons exist. So that's coming, and this will help, again, lay the groundwork for that. So there are 4 different shapes of suborbitals. So we've got the s orbital. The s orbital is this sphere. And it's a sphere, these 3-dimensional, I think these drawings kind of help show some of that 3-dimensionality. Each suborbital can hold 2 electrons. And the s suborbital, there's only one s suborbital in every shell. So in the first suborbital, there's the first shell, so when we're doing the Bohr models, it can hold one of those, and there's 2 electrons, which is actually why the first shell in all atoms, if you remember, only has 2 electrons, but then it goes up to 8 and 15 and 12 and 30 or whatever. This kind of helps explain that. This is within each shell, within each level, S is the best place for electrons to be, but it can only hold 2. So if you have an element that has 3 electrons, like lithium, it has to jump up to the next energy level. And eventually, as you get higher up, you're going to have to start filling out p orbitals. P orbitals are this shape. It's kind of maybe hard to see on this, but they're essentially like 2 balloons tied together. And what's interesting about this one is if you take a sphere and you start rotating it around this XYZ axis, it looks identical no matter how you rotate it. So there's only one S suborbital. But if you take these p orbitals and you kind of rotate them around the axis, they actually will overlap with each other, or like they won't overlap with each other. That's the interesting thing. They'll all kind of connect together. You can in fact do 3 of those. So there are 3 p suborbitals, and they're aligned on the 3 different axes you can kind of see right there. These are the ones we're going to focus on the most for our purposes. There are also D and F orbitals. And if you look at them, they start getting less and less logical and sensical. I think these ones kind of make sense. The D suborbitals are kind of like 2 p suborbitals, like on a plane. So again, there's a whole bunch of different orientations you can put them in. But then there's this weird one in the middle that's just like a p suborbital, but with like a hula hoop. Or tutu, it's just weird. And then you get to the F suborbitals, which are just like insanity. So this is all stuff that's very cool if you're into that kind of thing. And again, if you look at these shapes, you're going to see them. Oh, hold on. Boop, boop. There you go. You can see some of those shapes. Like these spheres are obviously S's. These kind of shapes here are p orbitals. These are probably, that looks like an F to me. Oh, that's probably an F. That's a D. Yeah, you can kind of see these shapes repeated over and over again. Okay, so so the p orbitals, there's 3 of them per energy level, and they each can hold 2 electrons. That's 6 electrons total. The d orbitals hold 10 electrons, and the f orbitals hold 14 total because they have 7 different configurations. We're going to come back to this electron configuration thing in just a second. But this again is like a way of showing where each electron is. It's a way of noting exactly where you can find each electron. And the big lesson to take out of this is that this is why the periodic table looks the way it looks. When Mendeleev first put the periodic table together, and other scientists as well, they didn't know anything about this. But they were looking at properties of elements. And as it turns out, those properties are determined by these electron configurations, by these orbitals. And that's why the table looks the way it does. So when you read the periodic table, it actually gives you a lot of information, if you know how to read it, about how these electrons work and about how orbitals work. The actual going through electron configurations and writing them, we're going to do again in the next video, but I do want to show you a little bit more about this. So I'm going to grab 2 things. I've got some models here for you and a periodic table. So we got our periodic table. So taking a look at the periodic table, there's a lot of things to notice, but for our purposes, it looks like there's some specific shapes here. Like I noticed that there's this row of 2, and then we've got this big like block, and it's, if you count it across, it's 10. And then we've got this little section here, boop, that's like 6 across. And then we've got this bottom section here that's 14 across. So this is kind of like representing those different orbitals. So let me kind of walk you through the process. I have made these models here. So the way that this works is that s orbitals only have 2 electrons. And so that kind of corresponds with this column. And what it's kind of talking about is not, it's the valence electrons, which orbitals the valence electrons are in. So S is represented by like a circle. And so that's kind of this kind of S block. P orbitals, there's a total of 6 electrons in P orbitals. And that's what like this area here represents, because it's 6 across. D orbitals have a total of 10 electrons, which corresponds to this section. And F orbitals are 14 total electrons, which corresponds to this section. So let me kind of walk you through part of this process. So if you are trying to make a model of these orbitals, I have these paper cutouts that I like to use for these. So they're not perfect because they're not three-dimensional, but I think you get the gist. So this is what I use to represent an s orbital. So it's a circle, but pretend it's a sphere. So electrons, this is in fact the 1s orbital. So it's the first orbital. We've got the nucleus is right in the center there. I got a little plus sign to represent that. Just hold on, just adjust this camera slightly maybe. Ooh, without it shutting off. It'll do that sometimes if I poke it just the wrong way. Okay, is that better? Kinda. I was getting a lot of glare. Not much I can do about it. Oh, that's what I can do. Note to self later. Okay, anyway, that's the s orbital. I just, there we go. It's a little bit better. Not really. Okay, there's an s orbital. And again, this means that electrons, this is a place where electrons might exist. Two electrons can kind of fill this area. You might be able to find them within this area, or you're likely to find them within this area. So this orbital can hold 2 electrons. And so, it's driving me a little crazy. Okay, there we go. Yeah, so this electron can, this suborbital can hold 2 electrons. So this, if you were trying to do a model of hydrogen, hydrogen has only 1 electron. Its electron would be somewhere within this orbital. If you have helium, it would have 2 electrons in this orbital. The next thing is then going up to lithium. So if you want to start adding more electrons, you can actually kind of follow the periodic table. So here's hydrogen and there's helium. So that's the kind of 1s area. The next orbital, we have to go following the periodic table again, is 2. So the second row, this represents all of the electrons in the second shell. It looks like the first 2 exist within the s orbital. So basically there are no p orbitals in the first shell. So we have to go to the second s orbital. The way that these work is that they just get bigger. It's the exact same shape, they're just further away from the nucleus. So if you look at the s orbitals, they're all just spheres. That's it. They all still only hold 2 electrons. They're just getting bigger and further away from the nucleus. So the way I like to do it is I just plop this right on top. So this would be like lithium would have 1 electron in this orbital because it has 3 electrons total, 2 from below, 2 that we showed below. And then beryllium would be with two electrons in it. Okay. If you start adding more electrons, and you can see again, like you just keep adding more electrons on top. The structure, the electrons from, is a weird way of saying it. Okay, we'll keep going and I think it'll make sense. The next step is the p orbitals. So the p orbitals are kind of shaped like this, again, 3-dimensional instead of 2-dimensional. And once again, I think, let's see if you can see this. If you had to take all 3 of these, imagine them in 3 dimensions, you could kind of put them like this, right? And they would all, none of them would overlap. It'd just kind of be there. Maybe you can see it better this way. Yeah. So kind of like, yeah, it's like this, 3 dimensions. So in 3 dimensions, that's what it would look like. If I'm just putting it on the 2 dimensions, I do it like this, just to show again that they don't really overlap with each other. Each one of these can hold 2. So as we go across the periodic table, we can see that the second shell doesn't have any d orbitals. It just has it has p orbitals, s's and p's. So all of these elements, as we start filling in more electrons for each of them, it just starts occupying more and more of these orbitals. So what's, I guess, important to note here, this idea that there are these different orbitals. Electrons fill them in particular orders. There's certain energy levels or certain orbitals that are more energetically favorable, that electrons prefer to be in, and that they kind of stack on top of each other. Once you've filled a shell, if you remember the second shell from Bohr models can only hold 8 electrons. And if you look, each of these 3 holds 2, so that's 6. And then the s orbital holds 2, so that's 8. So this is actually why we have the octet rule, because of these orbitals. Pretty crazy. If we get to the third shell, it starts to get a little bit more complicated, but before it gets more complicated, it stays exactly the same. The third shell also has s orbitals and p orbitals. They're just bigger. So those are the p orbitals from 3p. This is the 3s orbital. So again, if you need to start adding more electrons, it just gets bigger. And that's pretty much the principle behind all of this. So what we'll do next time is we'll go back and we'll, in the next video, we will go through the electron configurations. There's a couple of different ways to write those, because drawing out these models would be ridiculous. No one ever does this. I just like to do it as a visual. There are no packet pages for this particular section of notes. This is the prep work so that you understand what orbitals are, and then we can learn about electron configurations. So it's a little bit more conceptual. I will show you, let's see if I can find, is it on YouTube? Where's my YouTube? Hold on one moment, please. See if I can find this. Here we go. There's a couple of YouTube videos that are in my channel that might be helpful, and I will, I'll post them for you. There's a crash course on the electron, which could be kind of nice. This understanding the atom video, it's long, it's 35 minutes long, but if you skip to 12 minutes in and you watch, it kind of goes through, some really nice examples of this idea of orbitals, and especially this is the orbital, one of the kind of configurations or diagrams that you might want to know about. So yeah, it's pretty, there's little sections of this that are actually quite helpful. But yeah, starting at about 12 minutes. So if you want a different, like animated kind of 3-dimensional video, that one's pretty helpful. All right, so next video, more configurations, and we'll keep plugging along. Thanks, y'all.